Okay, in this video, we're going to look at question 8 on the worksheet. It says, consider the vector functions u of t, which is 4t minus 7i plus cos t k, and v of t, which is e to the 2ti plus t squared j minus the natural log of t plus 1k. Compute each of the following quantities. Okay, so in part A, we're going to take the dot product of the two vector functions, and that's going to give us just a function of t, and then we're going to differentiate that function with respect to t, and then evaluate that derivative at t equals 0. And then in part B, it's very similar. We're just going to replace dot product with cross product. Okay, so seeing the derivative of a product likely brings the product rule from Calc 1 to mind. And it does turn out, although I'm not going to go through the proofs in these videos, you can see a proof in the textbook, that there are actually two types of product rule here for vector functions, as you see below. Okay, so the derivative of the dot product of two vector functions u and v can be computed as follows, right? It's just u prime of t dotted with v of t plus u of t dotted with v prime of t. Okay, and then likewise here for cross product, u prime of t cross v of t plus u of t cross v prime of t is the derivative of the cross product of u and v. All right, so let's go ahead and apply these. So in 8a, okay, so I'm going to go ahead and first, right, note that I'm going to differentiate this dot product so that product rule applies, and then I want to evaluate, right, this expression at t equals 0. Okay, so why am I writing it out in this way? Well, the nice thing here is that I can avoid a lot of algebraic simplification by just computing each one of these quantities on its own. So u prime of 0, v of 0, u of 0, and v prime of 0. If I know those on their own, then just subbing them into this expression will just give me something numerical I have to simplify, right? I can avoid all that potentially messy algebraic simplification. Okay, so let's go ahead and do that. So u prime of 0, well, off to the side here, go ahead and compute u prime of t, and that's going to be what? The derivative of the I component, that's just 4, so 4i, and there's 0 for the j component. And then for the k component, the derivative of cosine, well, that's negative sine, so I get negative sine tk. So if I plug in 0 then for t into the derivative, I just get 4i, right? Because the sine of 0 is 0. So that's nice, right? U prime of 0 is just 4i. Okay, what's v of 0? Well, just plug 0 in for t into the vector function for v, and you're going to get e to the 0 I, so that's 1i plus 0j minus the natural log of 1, k, and the natural log of 1 is 0. So in fact, v of 0 is just I. Oh, okay, so that's really nice. U of 0, well, if you plug 0 in for t and for u, that's going to be negative 7i, and then plus 1k. So negative 7i plus k there for u of 0. V prime of 0, well, differentiating v of t off to the side, right? V prime of t is 2e to the 2ti, don't forget the chain rule factor, plus 2tj minus 1 over t plus 1k. Now plugging in 0 for t there, I get that v prime of 0 is 2i minus k. So I plug that in there, and now, right, I have some pretty easy dot products to compute. So 4i dotted with I, I'm just multiplying the I components there, so that's just giving us a 4. And then to compute this dot product, we'll multiply the I components, so negative 7 times 2 is negative 14. And then, right, 0 for both for both j components, so that doesn't contribute anything. And then for the k components, it's a 1 times a negative 1, so that's a negative 1. So I get 4 minus 14 minus 1, that's negative 11. All right, so not bad. And do keep in mind, this is a lot simpler than, say, computing u of t dot v of t in terms of components, then differentiating that resulting expression, then plugging in 0. Okay, this is a lot more efficient. Let's do a similar thing now for part B, Okay, so up above, I've just recorded those 4 key vectors that I needed in the last computation. And see, we're just applying that similar product rule. Now I'm just replacing dot with cross product, and those 4 vectors again show up here. So now let's go ahead and punch those in. I'm looking at these cross products. Now I could compute these cross products using determinants. That would be fine. But we could also do this using the ijk property, right? We looked at back in section 12.4. Okay, so first off, note I have an I cross an I here, right? I cross an I is 0, right? Any vector cross itself is the 0 vector. Okay, so then what can I do? Well, here I can expand, right? Because the cross product is distributive. So I have negative 14 I cross I, which just gives me minus 14 times the 0 vector. Then I'm going to get plus 7 I cross k. Now, from over here, I cross k, I need to go backwards. So I cross k would be negative j. So positive 7 I cross k is really negative 7j. All right, and so then what are we going to get? 2k cross I. Okay, from the next distribution, and what's k cross I? Well, here I'm going k to I, that's j. So k cross I is j. And then lastly, minus k cross itself, and that's the 0 vector. So when all is said and done, I have minus 7j plus 2j is minus 5j. All right, not too bad. And that does it for this video. Thanks so much.